joining, everyone. If you didn't know my name already, I'm Kegan, and I'd like to present about this project that I've been involved with for the past year, which I just summarize as it's an unknown target 3D model generation. But this presentation is going to be a bit more about this kind of a reflection on my 290 experience as a whole. So a little bit less research, a little more just kind of lessons learned and such. So hopefully it'll be a bit more of a casual presentation today. So just real brief, I'm going to start with just the background to this project, why I was interested in it, the overall problem statement, and very broadly just journey, what kind of things I went through this past year, and then finally just the lessons learned. Also, I worked on this presentation on my desktop at home, and converting it to my laptop messed up the formatting a little bit, but so some things are out of order, but hopefully it'll fun. So my main interests was actually looking into the space debris problem. It's kind of a looming threat for the space industry. Some statistics, these might be a little bit outdated, but about 27,000 pieces of orbital debris are tracked by the Space Surveillance Network. Apparently over 6,000 satellites orbit Earth, and 60% of them don't work. In the coming years, there's going to be many more satellites launched. So this is a kind of a part of the industry that perhaps needs a little more attention. Now, there isn't really as far as I've seen, there isn't one accepted solution, but one straightforward solution is, let's have a satellite interact with debris and just remove it from orbit. And while I was thinking about this, I was like, okay, how would you actually go about doing this? The first kind of roadblock I ran into was, okay, you have an arm, but where are you going to grab the debris? What's the best way to approach it? How do we even know what it looks like? And that was kind of my motivation to get more involved with this project. Sorry, this was out of order, but the top was supposed to be a video of Intelsat exploding. But this is an upcoming, I think, Clear Space One by ESA concept where it's exactly that, where they're trying to grab the debris. So how does this relate to SLAB? So the current, I say the most kind of relevant accomplishments are, one, the 3D pose estimation using neural nets, which is current rep for that is Jeff, and then the model generation and characterization using cameras, commonly summarized or abbreviated as SNAC, whose current rep is kind of Kegan. And on the left, the lab was able to, get 3D pose estimation of a known satellite target. We already knew what the wireframe of it looks like and what it generally looks like. On the other hand, on the right, you have an unknown asteroid that was, the model was built from structure from motion type algorithms, but it's large. It's like a potato. The approach will be a little bit different. So can we take kind of these ideas and bring it a little further to generate a 3D model of an unknown spacecraft? So problem statement. So this is the the sentence I've been using throughout all my presentations to Professor Nico. Provided a basic primitive shape model of a target and a noisy point cloud model of the same target, develop an algorithm that outputs an accurate 3D model of that target. So graphically speaking, we have maybe some kind of coarse primitive shape model that a neural net generated. And we get a noisy point cloud from something like structure from motion. It's a little bit confusing because these aren't satellites, but just imagine this is a satellite. But if we combine this information together, can we get something better? So that was kind of the idea behind this project. And I'm going to come back to this problem statement later, but for now, this is what I have. So the broad approach is, we have two inputs to our algorithm. We have, again, the coarse primitive shape model, and this is supposed to be generated by a neural net. And if you may remember, Jeff presented on something similar to this a couple meetings ago. And then the second input will be a noisy point cloud model from something like structure from motion, which I will be provided by someone like Kegan. And so the proposed algorithm, there's, again, very broadly, just two steps to it. One is we need to align the two models so that we're able to create a correspondence between them. So is this point, where does this point lie on the primitive shape model? Is this an edge? Is this a corner? And the second step will be once that alignments, that correspondence is created, we can generate the model, refine the model, make it better, and then hopefully the output would be an accurate 3D model. So I started thinking about this in fall quarter, and I quickly picked up on a few lessons learned. One, the first AA290 quarter will be a literature review. I am not a computer vision expert. I took CS231A last year, my first year here. And I went straight into this computer vision project, and I did not really know what I was doing for the most part. And I feel that, and after talking to many of you in the lab, I think most of you agree that the first quarter was just getting familiar with the material. So I don't think anyone here is new to 290, but if there was, my advice would be do at least 2 quarters of 290 because that first quarter is just going to be you trying to get familiar with whatever's out there. The second thing I learned was get a reference manager. Now I'm sure everyone has a different approach to this, but for my first quarter, the approach was download a bunch of PDFs, and I had a ton of previews open on my Mac, and it was a terrible way of managing all the papers I've been reading, like taking notes. I lost track of what was the name? It's A370 or whatever the default name you downloaded with. And then, actually, I gotta give credit to you, Caitlin, because you're the one who suggested check out Mendeley Reference Manager. It's free through Stanford, and I downloaded it. And my only regret is I didn't do it earlier because you can upload a PDF to it. It'll automatically extract the title and the authors, and there's a built-in UI for taking notes or highlighting. So again, I don't think anyone here is new to 290, but if you were, I would suggest at least look into a reference manager. There's Mendeley, and then there's if you're more open source oriented, you can go to Zotero. But I've also heard that people just use Google Docs to just include links. So, but yeah, managing your papers, your references, very important. So back to the actual project. First want to focus, take it step by step. So let's focus on the model alignment part. So typical formulation to solve the model alignment problem is actually right there on the first line. Given model 1, model 2, which are of the same target, and n corresponding position vectors. So typically this is for a point cloud, each position vector is point. You want to solve for the rotation r and the translation vector t that minimizes the following. Actually messed up. This should be the L2 norm of this. But the idea is R1 R2, that this first vector corresponds to this vector. It's just you need to rotate it and translate it so that they're as close as possible. And you try to minimize that. So this is actually a pretty common problem. It's called the registration problem. It's used in SLAM, in robotics usually. But for this problem, we actually needed to consider the scale, S, because the neural network output does, it only gives you the general shape. It doesn't tell you how big the target actually is. So that was the only kind of twist to this problem, where you had to add this scalar factor S into this optimization problem. So the solution I found to this was someone developed this algorithm called scale adaptive ICP, where, just for a little background, ICP stands for iterative closest point, and it's an algorithm, a really famous algorithm that's used to solve actually that first problem, the common problem. And so scale adaptive ICP is just a variant of that also just considers the scale factor. So this is for this ICP takes two point cloud model inputs typically. So we can convert a primitive shape model to a point cloud pretty easily by just evenly sampling the surface. And because it is an iterative method, you need a pretty good initial solution. And to achieve that, we can just take advantage of kind of mass properties. So the initial translation, we can just align the center of masses of the 2 point clouds. Initial rotation, we can align the principal axes. And then for the scale, we can scale by the square root of the ratio of the moments of inertia. And I tested this on two different models. Top is the well-known, I'm sure you're all familiar, it's Tango. And then the bottom is Dart, which I found on like some NASA open source website. So the Lyman results, it actually did pretty well, which was nice. You can see how so this top is Tango, and you can see the primitive shape model is just a box, and then it was able to kind of like try to fit it as well as it can onto here. And then for Dart, this is kind of from like a side view of it, but as you can see, like it went from this tiny thing and it blew up into fit the point cloud as well as it can. But even then, there are some downsides. It's actually really hard to see here, unfortunately, but if I had like a better contrast to this, you can see that this edge doesn't reach all the way out to the point cloud. If I take it from a different angle, you can probably see that it's like slightly out of alignment, like it's not perfect. So even amongst so obviously the point cloud itself is noisy, but you have to consider the fact that the primitive shape model has some noise to it as well, where the dimensions might not be quite right, the angles might not be quite right. So yes, I have a few more lessons learned. Something that Professor D'Amico actually warned me about was I actually took the scale adaptive ICP code directly from a paper. It was just like available on GitHub or something. But he warned me that if you don't implement it yourself, you're not actually understanding what's happening. And I did tend to have this bad habit of just taking an existing algorithm or paper and just trying to fit it to this problem. But that's not how innovation happens. So just to summarize it as well as I can, it's like try to balance innovation with what's been done before, because you also don't want to waste time re-implementing something that's already been established, that's available in some library. And I've had this conversation with Mason, actually, where I asked him, how do you think you can be a better researcher? And he said, try to use more what's available, which was the exact opposite problem what I had. So I don't really have a great idea of like advice for how to balance this, but finding that balance is like something that I found was an important thing I need to do. And the second thing is make sure you can visualize your results, especially for a computer vision project, because for checking the alignment, I could have some metric like, sorry, I'm gonna go back a little. Like, this is kind of like, could be a metric for how good my alignment is, like how small is this number. But it's kind of easier to just be like, oh, yeah, that looks pretty good. Like, this alignment looks pretty nice. And not only does it help to as like a checkpoint for you, but for when you're presenting to other people, because I could be wrong with the ratio here, but I feel like half the battle in research is just convincing other people that what the work you did was worthwhile and is worth their time. And you can't really do that unless you can show them what you did, your results. So, making sure you can visualize your results, I feel, is almost as important as doing the research itself. Probably research maybe is a little heavier there, but someone with more experience can probably comment better on that. Okay, so anyway, so the model alignment, I was like, okay, cool. We got a pretty good result. We can move on to the actual model generation. Now, the first thing to consider is, okay, what kind of model do we want to output? And there's so many options. There's, okay, do we want primitive shapes, which are, like cones, planes, cylinders, things like that? Do we want super quadrics, which kind of summarize all of those, but you can like kind of tune the parameters and make different types? Do we want a mesh, the most standard? Do we want voxels? And there's so many different options with different pros and cons, but why can't I choose one? Because I was really struggling with this, like, oh, which direction should I go? What's the best? And this is where I kind of go back to my problem statement. My problem statement wasn't that good. I think now, after I kind of went through this, I just wrote an accurate 3D model, and that doesn't really tell you what it's like trying to go for, like how accurate, what does accurate mean? What I probably should have done more is like kind of ask myself questions like these, like, does our model have limitations on memory? How small do our features have to be before we don't really care about modeling them? What is the goal of our model? Do we want the dimensions, the mass properties, or do we want to just find some kind of handle we can grab onto? And again, Professor D'Amico warned me about this in our meetings, but I think I was just a little naive to understand why this kind of language should have been fixed earlier. Because when I was posed with this question, I was like, oh, I have so many options, but I don't know what the best one is because I wasn't specific enough about what I'm looking for. So that kind of goes to my fifth lesson learned is, I think the best way for me, maybe some of you have different opinions on this, but I think including requirements in your objectives, like writing, is saying like, okay, this model model should have up to like 10 centimeters accuracy or something, and being a little more specific about what you're looking for, I think could have really helped me kind of guide me in my research journey. And then, going beyond the types, there's also the methods. I first looked at Ransack, which is a good way to like reduce outliers or not consider outliers in computer vision. There's projection-based point cloud refinement. So I was thinking, okay, maybe I could refine the point cloud by using the primitive shape model, like projecting it onto the primitive shape model. Gaussian mixture models, I was kind of struggling with using the primitive shape models of prior, so I was like, oh, let's take a statistics-based approach, which is like using Gaussian mixture models. And then there was more like just active contoured surfaces where they slowly kind of fit a mesh over an edge. Super quadrics, you know, updating that because they're a little more general. They can fit to a lot of different shapes, and shapes that are very present on satellites. But again, the problem with this is all of these have different outputs and inputs. Ransack is typically more primitive shapes, you know, fitting planes and shapes. Active contoured surfaces, that's a mesh output, so maybe you won't be able to capture edges as well. So I was really kind of just struggling and stumbling over, being like, oh, which direction do I go? I don't really know what the best option is. And it kind of brought me back again to like the problem statement where, okay, for example, my input point cloud, does it look like this or does it look like this? And the thing was, I wasn't quite sure, and you know, based on how the input point cloud is, you know, it might change my approach a little bit. Like this one is a little more on the left, is a little more uniform. On the right, it's much more concentrated towards the edges and the corners, which, you know, both of these I feel like you can take advantage of the information they provide, but how do I know what assumptions to make if I don't truly understand my inputs? So kind of going back, it was like, okay, what is my input primitive shape model and what is my point cloud model? What kind of assumptions can I make about it? And I was, I kind of just started a project with, oh, I'm just gonna get one from Jeff, I'm gonna get one from Caitlin. I don't really have to worry about it, but it wasn't until I got to about now where I realized, you know, that probably wasn't the best approach. And again, Professor D'Amico warned me about this very early on, but I was a little too naive to understand kind of the pitfalls of this problem statement. And I didn't truly understand, I feel, what my inputs were as well as what my outputs were. So again, I spent a lot of this quarter kind of just struggling to like narrow down on ideas and stick to a model generation method. And that's partially because, yeah, I was like, okay, I had a really broad search space. I didn't really know what to focus on. But also I had this kind of bad habit of not really committing to a specific idea, because I think I tended to have an idea and then I would eventually short circuit it by saying, oh, this probably won't work. Let me move on to the next thing. And again, I don't think that's how research is supposed to go, because the whole idea is you don't know what's going to happen with your approach. And you have to be okay with the idea of, you know, I might put in a lot of work and it might just not work. And that's kind of a difficult concept to kind of accept, I feel. And I wasn't really able to kind of see to the end a specific idea. And at the end of it, I don't really have anything. So last lesson learned, I'd say, you know, stick to an idea, have faith in it, make sure you see it to the end, even if it might not work out. So finally, just, you know, a little reflection, and thanks to everyone. Unfortunately, I don't have much to contribute to SLAB from this project, but I did learn a lot. I made a lot of mistakes, but I guess I figure, you know, that's part of what I hear in school. Learn, best way to learn is like you make mistakes. So I was offered that opportunity. I'm grateful for that. Plus, I'm a master's student, so whatever I do doesn't really matter too much. But I did learn a lot, and not only did I learn a lot. The model alignment portion of this project I did in C++ actually, and for one of my job interviews, they asked me, do you have any projects that you did in C++ that we can look at? It's like, I do. So I did well on that interview, and I actually got a job from it. So I will be working on the Spice toolkit at GPL after I graduate, and it's partially thanks to the opportunity I have here. So thank you, Professor Miko, for the opportunity, and thanks Caitlin and Jeff for being kind of the first people I would consult on this project, and everyone else that made me feel welcome in the lab. Thank you very much. And yeah, that's my presentation.